All right, get ready for this. We are about to go on a trip down a rabbit hole, a journey into one single devastating problem that literally shook the foundations of logic, of math, and maybe even all of science. It's this incredible story about a search for absolute certainty that instead led to a paradox so deep, so weird, that we're still wrestling with it today. I know, that sounds a little dramatic, but seriously, back in 1901, a philosopher and mathematician named Bertrand Russell stumbled upon a problem, a tiny crack in the bedrock of logic that threatened to bring the entire building crashing down. And it all started with this huge fight over what numbers even are. So in one corner, you had thinkers like Immanuel Kant. He basically argued that math is something we humans made up. It's a powerful tool, sure, but it's a construction of our minds. It's subjective. But in the other corner, you had guys like Gottlieb Frege and Bertrand Russell, and they thought no way. For them, math had to be objective. It's a part of pure logic, something that exists out there in the universe, just waiting for us to discover it, kind of like a law of physics. Now, to win this argument, to prove math was truly objective, Frege and Russell had a massive task ahead of them. They needed to boil all of arithmetic down to its most basic logical ingredients. And to do that, they had to answer one of the simplest, but also deepest questions you can possibly ask. What is a number? I don't mean the symbol 4, I mean the idea of fourness itself. And their answer? Oh, it was brilliant. It was so elegant. They said, look, numbers aren't some mysterious abstract thing. They're just sets. The number 4, for instance, is just the set of all sets that have 4 things in them. This idea was a total game changer, and it was all built on this new, powerful field of math called set theory. So, to really understand how this beautiful system came crashing down, we first have to get our heads around what a set actually is. And you know what? The basic idea is incredibly simple. That's it. A set is just a collection of stuff. The guy who invented set theory, George Cantor, called it a gathering together into a whole of definite, distinct objects of our thought. But I think a better way to put it is this. A set is a many that we can think about as a one. And this is what makes sets so incredibly powerful. The things inside a set, the elements, they don't have to be related at all. You can have a set containing LeBron James and, I don't know, the top half of the Eiffel Tower. The elements don't even have to be real. You could have a set with the number 4 and Harry Potter. Basically, if you can think of it, you can stick it in a set. So the rules for this whole new system seemed totally straightforward, almost like common sense. Rule 1, you can make a set out of any collection you can imagine. And the other rules are just as simple. A set is defined only by what's inside it. The order of the stuff doesn't matter, and repeating something doesn't change the set. It all seems perfectly fine, right? But there was one more little rule, a consequence that followed directly from that first one. And here it is. This is the one, the tiny little rule that breaks everything. It makes perfect sense, logically. If you can make a set out of anything you can think of, and you can obviously think about sets themselves, then you can have sets that contain other sets. And if that's true, well, then you can have a set that contains itself. It sounds a little weird, but it seems to follow from the basic idea. Now, this seemingly harmless idea is exactly where Bertrand Russell's mind went. He started playing around with this idea of sets containing themselves, and in doing so, he stumbled into a logical black hole, a paradox that would bring this entire beautiful project to a grinding, catastrophic halt. Okay, so Russell started by imagining all the sets in the universe sorted into 2 big piles. In the first pile, you have all the normal, boring sets, the ones that don't contain themselves, like the set of all cats, for example. That set is a concept, not a cat, so it doesn't contain itself. Easy. But in the second pile, you have all these weird self-referential sets that do contain themselves. For example, the set of all sets is itself a set, so it belongs in its own collection. Or how about the set of everything I'm thinking about right now? Well, since I'm thinking about that very set, it contains itself. This is where Russell makes his genius, fatal move. He decides to create a brand new set. He takes every single set from that first pile, all the normal, well-behaved sets that do not contain themselves, and he scoops them all up into one giant collection. We'll call it Russell's set for short. And this question is the bombshell. Russell just looked at his new creation and asked a devastatingly simple question about it. Does this set, the set of all sets that don't contain themselves, does it contain itself? Now think about it. There are only 2 possible answers here, right? Yes or no. And here's the crazy part.
Both answers lead to a complete and utter logical meltdown.
Let's walk through it. Possibility 1. Let's say, yes, it contains itself. Okay, well, what's the rule for getting into this set? The membership card literally says you must be a set that does not contain itself. So if it does contain itself, it violates the one and only rule for entry. It has to be kicked out. So if it's in, then it must be out. That's a flat-out contradiction. Impossible. Okay, fine. So yes doesn't work. Let's try possibility 2. No, the set does not contain itself. Well, let's check the rule again. The rule is you have to be a set that doesn't contain itself. If our set doesn't contain itself, well, then it perfectly fits the description. It qualifies. It has to be included in the set. So if it's out, then it must be in. Another complete mind-breaking contradiction. So Russell writes about this paradox in a letter to Gottlob Frege, the guy who had just spent years of his life writing his masterpiece based on this very system. And you have to feel for Frege. When he read that letter, he was, in his own words, thunderstruck. He had a physical breakdown because he saw instantly that this wasn't just a clever trick, it was a fatal flaw. It required, as he put it, the demolition of his entire life's work. So, the very foundation of mathematics has a giant, paradoxical hole blown right through the middle of it. What do? Well, mathematicians scrambled. They desperately tried to patch the hole, to find some way to save the whole system from this self-destructing logic. The most popular fix was, well, pretty straightforward. Just get rid of the rule that caused all the trouble in the first place. Mathematicians, including Russell himself, came up with new systems of set theory with one big new restriction. Sets can never, ever, under any circumstances, contain themselves. Problem solved, right? But hang on a second. Does that really feel like a solution? Can we just change the rules of logic because they lead us to a place we don't like? The argument against this is that those original rules weren't just made up. They seem to describe something fundamental about how we categorize the world, about how we think. You can't just ban a rule if it's a reflection of something true. And this is where it gets really fascinating. Because it turns out Russell's paradox isn't just some abstract problem for mathematicians in ivory towers. The exact same paradox is woven into the very fabric of our everyday language. The parallels are just sitting there in plain sight in basic grammar. Think about it. A sentence has a subject and a predicate. Garfield is a cat. Garfield is the subject, is a cat is the predicate. Well, a set is basically just a predicate. And a set containing an element is the same exact idea as a predicate being true of a subject. And just like with sets, some predicates are true of themselves and some aren't. The predicate is a cat is not true of itself. It's a phrase, not a cat. But what about the predicate is a predicate? Well, yeah, it is a predicate. It's true of itself. Or is a string of words. Yep, that's true of itself too. See, the self-reference is right here in the way we talk. So, what if we do the exact same thing Russell did, but with words? Let's invent a new predicate. The predicate is not true of itself. This new predicate would apply to all those normal ones, like is a cat or dunks, because they are not true of themselves. And this brings us right back to that final, inescapable, brain-melting question. Is our new predicate, is not true of itself, true of itself? Well, if it is true of itself, then by its own definition, it's not true of itself. And if it's not true of itself, well, then it fits its own definition perfectly, which means it is true of itself. We are trapped. It is the exact same paradox, and we can't just ban this rule in language. It's just how language works. So if our most fundamental tool for describing reality is itself inherently paradoxical, what on earth does that say about the reality we're trying to describe?